Are you able to see the screen?
Yes, sir.
Yes, sir.
So yesterday I started with RC phase shift oscillator circuit, right? We discussed about the circuit operation, and we also discussed about the merits and demerits of RC phase shift oscillator. Okay. Right. So today, let us consider the second oscillator circuit. Even this oscillator circuit belongs to audio frequency range category. Okay. And the circuit is called as Wein bridge oscillator, or in short, bridge oscillator circuit. Okay. The second circuit is Wein bridge. Okay. Now, in case of bridge oscillator circuit, okay, what you will have is, once again, the same arrangement. You will have an amplifier stage, and you will have a feedback stage. Okay. But in case of Wein bridge oscillator circuit, the feedback stage is consisting of a bridge circuit. So feedback circuit is consisting of a bridge circuit. Okay. And this bridge circuit is made up of RC elements. Okay. So once again, the feedback circuit is made up of passive elements. Okay. There are no active sources, passive elements. Okay. And in the amplifier section, you will have RC coupled amplifier. RC coupled amplifier. Okay. So RC coupled amplifier, you know, right? It is constructed on the basis of voltage divider bias circuit. Okay. Now, one noticeable difference in case of Wein bridge oscillator circuit is that the feedback circuit, or the bridge circuit, okay, feedback circuit or the bridge circuit gives 0° phase shift. Okay, it gives 0° phase shift. Now, as per Barkhausen criteria, we have seen that the angle criteria says that the total phase shift around the loop should be 0° or 360°, and mod of A beta, that is the loop gain, should be unity. Okay, loop gain should be unity, can be maintained by tuning the value of beta. Now, how will you ensure that the total angle remains 0° or 360°? Okay, given the fact that the feedback circuit gives 0° upfront phase shift. Okay, so if the feedback circuit gives 0° phase shift, that means to say this amplifier circuit should also be giving 0° phase shift. Okay, now the question is, RC coupled amplifier, when it is operated in common emitter mode, okay, you know that a single stage RC coupled amplifier, okay, that's the reason I'm writing it in a different color. So single stage, let us put as hyphen, single stage RC amp gives how many degrees of phase shift? 180° of phase shift. You have already seen, right, in case of RC phase shift oscillator. So single stage gives 180° phase shift, but you want your phase shift to be 0°. So how do you compensate for this? Can anyone tell me? You cannot go for a simple single stage RC amplifier because it gives 180° phase shift, and the feedback network will not give any phase shift because it gives always 0-degree phase shift. So the Barkhausen criteria is not satisfied. So how will I, come out of it? Can anyone tell me? Can anyone propose the solution? You can type your answers. So that means to say there is a shortage of further 180-degree phase shift. So how will I introduce that further 180-degree phase shift? Because if I introduce further 180-degree phase shift, the total phase shift becomes 0-degree plus 180-degree plus 180-degree, that is 360-degree. That can be considered as 0-degree itself. Rakesh, any solution you are thinking of? Nirja? Shashank, can anyone tell me? How to introduce further 180-degree phase shift? Yashaswini or
So
Divin?
by increasing capacitances and resistances in feedback network.
Okay, but I have already told you, right? The bridge network always gives a 0-degree phase shift. So there is no scope to, what do you say, increase or decrease the phase shift. It is fixed. Because the mathematics proves it, that whenever you use a bridge network using RC element, it always gives a 0-degree phase shift or very close to 0-degree phase shift. So you cannot touch the bridge network. So what you have to do is you have to do with the amplifier. See, if single stage amplifier gives 180-degree, what you have to do, you have to go for a second stage. So you can go for 2-stage cascaded amplifier. Okay, now what do you mean by 2-stage cascaded amplifier? Okay, let's say this is your stage 1 RC coupled amplifier. This is your V in and this is your V out. Let's say your input is positive going, okay? This is Vi. V01 I will write. So V01 going to be a signal which is phase inverted by an angle of 180-degree, right? So this is the nature of V01. Now, if you feed this inverted signal to the input of second RC network, what happens? Again, this RC network further gives 180-degree phase shift. I mean, RC coupled amplifier, I'm saying. Okay, let me write amp and amp. Okay. So the first amplifier gave 180-degree phase shift. That's the reason a positive going input became inverted one, right? Now what are you doing? You are feeding a negative going signal to the input terminal of second stage RC coupled amplifier. And upon receiving this signal, the second stage RC coupled amplifier gives you a different output, V02, and V02 will be a phase corrected one. Phase corrected one. So in case of Wein bridge oscillator, what we do is we go for a 2-stage RC coupled amplifier. Okay, so the drawback going to be something like the circuit going to be big, right? The circuit going to be big, but still, it gives 0-degree feedback between the input and the output. Okay, now you compare the input and output. So let me put it in within the cloud. Okay. So this is your input, your ultimate input or the first input, okay, to the 2-stage RC network is a positive going one, and your ultimate output V02. Okay, if you look at this is also a positive going one. So angle phi, okay, between Vi and V02 is equal to 0-degree, right? Both are starting from 0-degree and completes its positive half cycle at 180-degree and then completes the negative half cycle at 360-degree. Okay, so this is how we overcome the phase shift problem in case of Wein bridge oscillator circuit. Okay, fine. So having understood this, probably we can go to the second section. Okay. So, all right. So let me just draw the basic circuit first. Okay. So basic circuit for Wein bridge oscillator or Wein bridge oscillator. Okay. All right. So as I was mentioning that it takes the shape of a bridge. So what I will do is, let me just construct the bridge. Okay, something of this kind you can construct. Okay, so this is, say, C1 and this is R1. Okay, so here you will have R3, and in this branch you will have the series and parallel combination of capacitor and resistance. This is C2 and this is R2. Okay, and in the final arm, once again you will have R4. Okay, so this node is grounded. This is the reference node. Okay, so this is node 3. We'll just name the nodes. Node 1. Okay, this is going to be node 2, and the final one going to be node 4. Okay, and here you will have your amplifier stage. Okay, this is your amplifier circuit. All right, now the amplifier circuit will have the input port, and it will also have the output port. Okay, so one terminal is grounded. Okay, so this is your output of the amplifier. Okay, let me write, this is amp output. Okay, so the output is connected across node 1 and 3. The output of the amplifier is connected across node 1 and 3. So let me write, output of amp is connected across the node 1 and 3. Okay, so 1 is here, 3 is ground, right? So this ground and this ground going to be the same. All right. And next comes the feedback signal, right? This feedback signal from the feedback circuit. Okay, so this is where you derive your feedback signal. Okay, so which is observed across the parallel combination. So this is your VF. Okay, this is the fixed nomenclature. Okay, I mean, you cannot interchange, because that's how the circuit has been built. Okay, if you interchange the oscillator, action may not take place. Okay, fine. So this 4 is kept at the lower potential. Node 4 is at lower potential, and node 2 is at higher potential. All right. So this is the basic circuit of Wein bridge oscillator. Okay. Now let me propose the actual circuit. Okay. So why I have proposed basic circuit is to clear off the doubts. Okay, if I were to draw the bigger diagram, you would have had many doubts. Okay, just for the sake of clarity, I have divided my explanation into 2 parts. Okay, so first I have proposed the basic circuit. Now I'm going to propose the actual or exact circuit. Now, while drawing exact circuit, what I'm going to do, I'm not going to change the bridge circuit, right? Bridge circuit is complete. I have provided each and every element over here: series RC, parallel RC, and the remaining two arms of the bridges, everything being drawn over here. Okay, now what I haven't drawn completely is the amplifier circuit. Okay, so what I will do, now let me draw the amplifier circuit and then let me connect it to the bridge circuit. Okay, now in the previous discussion, okay, you have come to know that the amplifier circuit is consisting of two-stage RC coupled amplifier. So two-stage RC amplifier. So what I have to do presently is that I need to draw a two-stage RC coupled amplifier circuit, and then you can connect this amplifier circuit to the bridge network. All right then. So let me construct a two-stage RC coupled amplifier circuit. Okay, so in place of this black box, let me put it inside a cloud. Okay, draw a two-stage amplifier circuit. Got it? That's what we are going to do now. Okay, quickly let me draw. Okay, this is R4. Remember, this R4 is basically bridge resistor. Okay, this bridge resistor. Okay, I will give you a hint. I'll just color it with pink, and let us put that particular symbol over here also. So one arm of the bridge itself serves as the emitter resistor. Okay, and this resistor is a non-linear resistor which will help you in tuning the waveform to a sinusoidal value. Okay, and the rest all remains the same. Here you will have RC1. Okay. This is your, let's say, RB1. This is your RB2. These two are connected together. Okay. And we'll connect it to the bridge little later. Don't worry about it. Okay. So these two are connected together. Okay. Fine. Let us just extend the wire. Now, output of first stage. This is your collector 1, base 1, emitter 1. So output of first stage is fed to the input of second stage. So this is going to be B2. I will little correct this shape. And here you will have RB3, and here you will have RB4. These two are connected together. Your RC2 and RE2. Okay, this is a bypass capacitor. Okay, in the first stage there is no bypass capacitor. I will tell you here. Can you see? There is no bypass capacitor across R4. I'll tell you the reason also a little later. This is your coupling capacitor, say CC2, and this let us say CC1. Okay, let us join these two. And the common connection goes to the DC power supply, VCC. Okay, and this is your output. This is where you observe your output. This is V0. right? And this is grounded. This entire lower half is grounded. Okay. Now what we'll do, we will construct the bridge network. Okay. So somewhere here, let me draw the first node, the second node, third node, and the final node. Okay. Here I will have my series RC network. Okay. Say R1, C1, no problem. And this, let us take the parallel network. C2 and R2. Okay. And this going to be the R3. Okay. Fine. I will do the R4. You will not have any R4 here. You will have your R4 here. Okay. So let me do the remaining connection. So this is your node 1, as I have already shown you. Node 1. This is node 4. Okay. This is node 2, 3. Okay. And this is your the remaining circuit. It's okay. We will connect it again. Fine. So output of the amplifier. Okay, where is your output? Output is here, right? So this output, you need to tap and you need to give it to the bridge network. Okay. Here. So this is how you have connected your output. Now, node 4. Okay, node 4 is connected to the base of this amplifier. Okay, so what I'll do, I'll just use a different color. Let me use a jumper. Okay, so it is connected to the base of the first amplifier. Okay, now I am left with resistance R3. Now this resistance R3 is connected to R4. Let us use a jumper and we'll connect it to R4. Okay, this is how the connection is done. And the lower half is grounded, right? Lower half is grounded. You can show a ground connection over here. So this is your Wein bridge oscillator. Now, for the further analysis, let us consider the series leg as Z1 impedance and the shunt leg, let us assume it as Z2. Okay, you can use it interchangeably, not a problem. So series arm I have taken Z1 and the shunt arm I have taken Z2. This will help me in the further analysis. So that's the reason I have written Z1 and Z2 in the beginning itself. Okay, all right. And now let us also mark certain sections of the circuit. So this is your stage 1. This is your stage 2. Okay, and this part of the circuit is your feedback circuit. Okay, so feedback circuit gives 0-degree phase shift. All right, stage 1 gives 180-degree phase shift. And stage 2 gives further 180-degree phase shift. Okay. Therefore, the total phase shift amplifier section is 180 plus 180 is 0-degree. Okay, or 360, doesn't matter. Okay, so this is it. Okay, so this is the complete circuit of Wein bridge oscillator. Okay, two-stage amplifier connected to the bridge network. Okay, the bridge network we have already proposed here. Here, the only exception is that this R4, right? This R4, what we have done is we've directly connected to the amplifier section, right? So here it is, the amplifier section. Okay. Now, some important note. Okay. Now, R4 is unbypassed. Unbypassed. Okay. The reason for this intentional unbypassing is that you know that RC coupled amplifier gives very high gain. Okay. If bypass capacitor was used, stage one, the overall gain of two-stage RC amplifier would have been very high. We have seen, right, in module 3, in one of the problem, we had considered two-stage RC coupled amplifier. Okay, so the overall gain was something like 34,000 units. So imagine if you give 1 millivolts of input, you know, this 1 millivolts of input is going to get amplified by a factor of 34,000 units. So the signal may be very large, and there can be, you know, clipping action taking place at the output. Okay, that's because the output may be beyond the handling capacity of the amplifier itself. Okay, so the output may get clipped. So how will you ensure that the gain of the amplifier circuit is not very high? So that is by doing an intentional unbypassing. So if you don't use a bypass capacitor, what happens? The gain of the circuit reduces. Okay, once the gain of the circuit reduces, you know, you will be able to control the output amplitude of V0. Okay, so that's why in stage one there is no ceiling. Okay, so therefore the overall gain AV becomes AV1 into AV2. So AV2 is high due to CE, right? There is bypass capacitor in the second step. In both the stages, if you don't use bypass capacitor, then your signal would have been very, very small. So you need a bigger signal, but you don't need a very high amplitude one. Okay, so you need a moderate signal. That's the reason AV2 will have very high gain due to the presence of C, and AV1 will have smaller gain. Okay, that is without C. Okay, so therefore the overall gain is moderate. Okay, moderate, because you are multiplying lower value to a higher value. So the gain becomes moderate. Okay, if these two were to be a bigger number, then your AVT would have been in the range of thousands. Now the AVT will be in the range of hundreds. Okay, it will be in the range of hundreds. So that's the part. Okay, the another important part is R4. So R4 is not a conventional resistor. Okay, it's not a linear resistor, I meant to say. It's a non-linear resistor. Non-linear resistor. Okay, what do you mean by non-linear resistor? If there is some inductance associated with the resistor, then the response won't be linear. Okay, so the response becomes non-linear. Now, this non-linearity has shown the effect on output waveform that by tuning, okay, by tuning R4, a proper sinusoidal signal can be obtained. Okay. Now remember, R4 is a part of feedback circuit. Okay. So therefore, by varying R4, basically what are you doing? By varying R4, beta is varied. Okay, because beta is what the gain of the feedback circuit, and by varying the element of feedback circuit, indirectly you are varying the beta, and this will help you in getting A beta into A beta is equal to 1 condition, and when this condition is satisfied, sustained oscillation results. Sustained oscillation results. Okay. Okay, so this is the working of Wein bridge oscillator circuit. Okay. Next comes the frequency of oscillation. Okay. The frequency of oscillation we will derive in the end is, it's a RC network, right? In case of RC network, in network analysis, you must have seen F is equal to 1 by 2 pi RC, right? So basically you get 1 by 2 pi RC, since there are different R's and C's, so it is R1, R2, C1, C2. Okay. On the other hand, if you choose R1 is equal to R2 is equal to R, and C1 is equal to C2 is equal to C, then F would have been 1 over 2 pi RC, because R into R is R square, under root R square is R, under root C square is also C. So this is your frequency of oscillation. Okay. One for equal values of R's and C's, and the other expression is for unequal values of R and C's. Okay. Fine. Yeah. And there are some, what do you say, the standard conditions. Okay. The standard condition says that the beta value, okay, beta value for Wein bridge oscillator should be around 1/3. Okay. So when the beta value is around 1/3, what happens is that mod A beta, we know that should be greater than or equal to 1 for oscillations. Okay, it can't be less than, because if it is less than equal to 1, the waveform will die. Okay, greater than, it is okay, because you will get waveforms, and then by tuning the value of beta, you will be able to contain those oscillations for the constant value. Okay, so A beta should be greater than 1, and the condition is that beta should be around 1/3. So you can say that A should be greater than or equal to 1 by beta, or should be greater than or equal to 1 divided by 1/3, or greater than or equal to 3. So the amplifier gain should be greater than or equal to 3. Now you got the point, right? So amplifier gain, that is the gain of Wein bridge oscillator, should be around greater than or equal to 3. So you don't need a very high gain. Okay, so you don't even need hundreds of gain. So that can be ensured by minimizing AV1. Okay, so you need to play around with the resistance value RE. Okay, so sorry, the bypass capacitor as well as the feedback, the amplifier elements. that is RE, and with which you will be able to fix a very small value of AV1. Okay, so probably your stage 1 should give you less than unity gain. So basically your stage 1 should behave like an attenuator rather than an amplifier. Okay, so that's how it is done. Okay, in the sense, let's say this is 50 and let's say this is around 0.25. So 50 into 0.25. Okay, is about 12.5. Okay, so something of that kind you are supposed to achieve. That's the reason I said minimizing AV1. So if you start minimizing this AV1, you will be able to get lower value of total voltage gain. Yeah. So that is about Wein bridge oscillator circuit. Okay, the advantages of Wein bridge oscillator circuit is that circuit gives oscillations in the range of audio frequency range. Okay, and the other advantage is that variable frequency is possible. Okay, that's because in order to get variable frequency, you have to simultaneously vary the values of resistor as well as capacitor. In case of RC phase shift oscillator, you have had 3 resistors and capacitors. Varying 3 values simultaneously is difficult. Okay, so but varying 2 values simultaneously is possible. So probably what you can do is you can provide a lever for both resistor and capacitor, and by rotating the lever, you will be able to change the values of R1 and C1 simultaneously. So that is the second advantage. So first advantage is audio frequency range oscillations. Second advantage is that variable frequency is possible. Okay, and the disadvantages, there are a few disadvantages, something like it makes use of several elements, and due to which the circuit size increases, and the cost of the circuit is more compared to RC phase shift oscillator. Okay, and since the circuit is made up of RC elements, it is prone to electromagnetic interference because there is no shielding provided, and the aging effect may deteriorate the frequency of oscillation as well. So these are the disadvantages. Okay, all right, I'll stop my class over here. Okay, in the next class we can start with radio frequency oscillators. Okay.